Hi students, we have studied that there are four ways of handling deadlocks, right? So the first two ways we have already studied, that is deadlock prevention and deadlock avoidance. And the third way of handling the deadlock is deadlock detection. So in this approach we are allowing the system to enter into the deadlock. So what we are doing is we are not providing any deadlock prevention or deadlock avoidance algorithm. So if the system does not use either of them, the system may enter into the deadlock situation. So we are forcefully allowing the system to enter into the deadlock. So once the deadlock occurs, we will be using some algorithms to detect that deadlock, and also we are providing some algorithm to recover from the deadlock. So in deadlock detection approach we will be using two algorithms, one for detecting the deadlock, that is detection algorithm, and the second is recover from the deadlock, so recovery scheme. Okay. So here we are allowing the system to enter into the deadlock state. How to do that? If we don't provide any deadlock prevention or deadlock avoidance algorithm, then the system may enter into the deadlock state. So when we are not providing any deadlock prevention or deadlock avoidance algorithms, the system must provide two things. The first thing is an algorithm that examines the state of the system. So one algorithm is needed to understand the state of the system. What is the state? Whether it is safe state or unsafe state. Okay. So one algorithm is used to determine the state of the system, to determine whether a deadlock has occurred or not. So that is nothing but detection algorithm. And the second thing the system must provide is an algorithm to recover from the deadlock. So if it finds that deadlock has occurred, then we should provide an algorithm which recovers from the deadlock. So two things are required if we are not providing deadlock prevention or deadlock avoidance algorithm. Okay. There are two types of algorithms. The algorithm which deals with single instance of each resource type, and the algorithm which deals with several instances of a resource type. In deadlock avoidance algorithm we have seen resource allocation graph algorithm deals with single instance, and Banker's algorithm deals with multiple instances. In this deadlock detection also we are following the same approach. So if there are only one instances of each resource type, if there are only single instance of each resource type, then we can use a variant of resource allocation graph, which is very similar to resource allocation graph, which is called wait for graph. So the variant of resource allocation graph is called wait for graph. This graph can be obtained by removing resource nodes and corresponding resource edges. So if we remove resource nodes and appropriate edges in the resource allocation graph, then we would get wait for graph. So basically wait for graph is a version of resource allocation graph. So if we remove resource edges and their corresponding resource nodes and their corresponding edges, then we would get wait for graph. So in wait for graph, edge from Pi to Pj, the first point, Pi to Pj implies that Pi is waiting for Pj to release some resources which are needed by Pi. That means Pi is waiting for Pj. So in resource allocation graph the same thing would have written as Pi arrow some resource, and then that resource is being allocated to Pj, correct. So Pi to resource and then resource to Pj. That would have implied that Pi is waiting for Pj. But in wait for graph, we would write Pi arrow Pj. That means that Pi is waiting for the resource of Pj, or resource, yeah, which is holded by Pj. Okay, yeah. And H Pi to Pj exists in wait for graph if and only if, see, an edge from Pi to Pj exists if and only if there are two edges in resource allocation graph, that is Pi to Rq and Rq to Pj. If these two edges are existed in resource allocation graph, then only we can have Pi to Pj edge in wait for graph. Because if we remove Rq resource, if we remove this resource, then we would get edge from Pi to Pj in wait for graph, right? Therefore, if we want to have edge from Pi to Pj in wait for graph, then we should have two edges. Those are Pi to Rq and Rq to Pj in resource allocation graph. Okay. If we are provided with resource allocation graph, we can draw wait for graph. Then periodically invoke an algorithm that searches for a cycle in the graph. So after drawing the wait for graph, we need to search for the cycle in the graph. If there exists a cycle, then we can say that deadlock has occurred. This we have seen in resource allocation graph also, right? If the graph contains cycle, then it means that it is in unsafe state. But if there exists a cycle in the wait for graph, then it means that there exists a deadlock. Then there exists a deadlock. Is that clear? Yeah. An algorithm to detect a cycle in a graph requires an order of n square. It means that the time complexity of this algorithm is n square. N is nothing but number of vertices, that is number of processes in the graph. Yeah. See, this is our resource allocation graph. If we remove all the resources and their corresponding edges, if we remove all the resources and the corresponding edges, we would get wait for graph. See, we have this R1 to P2 and P1 to R1, right? Yeah, we can directly write, it means that from P1 to R1, R2 to R1 to P2. So instead of writing this edge, we can directly write it as P1 to P2. P1 to R1, R1 to P2. It means that P1 is waiting for R1, R1 is being allocated to P2. So instead of writing these two edges, we can directly write P1 to P2. Yeah. Again for P2 to R3, R3 to P5. So instead of writing P2 to R3 and R3 to P5, we can directly write P2 to P5. And again P2 to R4, R4 to P3. We can directly write it as P2 to P3. So remove all the resource nodes and their corresponding edges, you would get wait for graph. Is that clear? Yeah. Again, this algorithm can be applied only when there are single instances of each resource type. If there are multiple instances of each resource type, then we need to use an algorithm which is very similar to Banker's algorithm. So if there are several instances, if there are multiple instances of a resource type, then we have to use an algorithm which is very similar to the Banker's algorithm. So again, we would require some data structures as we had used in the banker's algorithm. So for this algorithm also we are going to use some of the data structures. The data structures are as follows: available, allocation and request. Available and allocation are same as in banker's algorithm. Available is a vector and allocation is an matrix. So I don't have to explain this again, right? So these are same as in banker's algorithm. Okay. One extra data structure we are using here is request. Instead of need, we are using request, and we don't have max data structure here. We have only 3 data structures. Available and allocation were also there in banker's algorithm. One extra data structure here we are using is request. Instead of need, we are using request. What is that request? This indicates how many number of instances are currently requested by the process. Means now at present the process is requesting how many more instances. It is requesting, it is not needed, but it is requesting. Need is different. Need means it requires these many resources in order to complete its task. But the request is, it is requesting for that resources. We don't know whether it is needed or not, but it is requesting. Understood the difference? Yeah. So if request of I comma j, it is I comma j, if request of I comma j is equal to k, then it means that process pi is requesting k more instances of resource type rj. So in need, the process pi needed k more instances, but here it is directly requesting. Pi is requesting k more instances of resource type rj. It is request of I comma j, okay, this one, I comma j. Okay, yeah, these 3 are the data structure which we will be using. Let's quickly see the algorithm. This algorithm is very similar to banker's algorithm, that is safety algorithm. It is almost same. Instead of need, we will be using request. Wherever need is there, we will be using request. Okay, yeah. Let work and finish be vectors of length. You know what is work and what is finish. I don't have to explain it again, right? Okay. So work is initialized with available. Yeah, this we had done in banker's algorithm also. And in the second step, for I is equal to, you can take 0 to n minus 1 or 1 to n. Both are fine. 0 to n minus 1 or 1 to n. If allocation, yeah, the extra thing here is, if allocation I is not equal to 0, then finish of I will be initialized to false. This was not there in banker's algorithm. If allocation of I is not equals to 0, then only finish of I is equal to false. Otherwise, finish of I will be set to true. If allocation I is equal to 0, then finish will be set to true. Why? Because if there are no resources are allocated to the process, then we cannot reclaim any resources, right? So it is as good as completed. You will understand this once I explain the example, okay? So if allocation, if means if there are no resources are being allocated to a process, then it is as good as completed, because we cannot reclaim any resources from that process. It is not holding any resources, so we cannot reclaim it. That's why we will be setting the finish of I as true for that process. But if the allocation is not 0, then obviously we can reclaim the resources. In that case, we will be setting finish of I as false. That means, yeah, it has not yet been completed, so we can reclaim the resources once it completes its execution. Okay, yeah. And in the second step, we have to find a process which satisfy both of these conditions. This is same as our banker's algorithm. We have to find a process whose finish of I is equal to false and request I is less than or equal to work. In banker's algorithm, it was need. Here it is request. Request I is less than or equal to work. Otherwise, if we can't find any such process, then we have to skip to the step 4. If we find such process, then we will be doing this. We will be updating our work, which is same as in banker's algorithm. Work is equal to work plus allocation I, and then after it completes its execution, we will be setting finish of that process as true, because it has completed its execution, so we can reclaim its resources. Yeah, this condition is nothing but reclaiming the resources, reclaiming the resource of that particular process. Understanding? Okay, go to step. So we are going to repeat this process until we cannot find any such process which satisfies these two conditions. Until then, we are going to repeat this process. Correct? Yeah. Finally, we will be checking the condition. If finish of I is equal to false for any of the process, if finish of I is false, means if any of the process is not able to complete its task, even after repeating the process, if any of the process is not able to complete its task, then it means that there is a deadlock in the system. Because once we have repeated all the processes, once we have gone through all the processes should be completed, right? It means finish of I should be true for all the processes. But if finish of I is false for any one of the process also, then we can say that there is a deadlock state. And also that particular process is called deadlocked. That particular process is deadlocked. We can say that that process is deadlocked because it is not able to get its resources and it is not able to complete its task. That's why that particular process is deadlocked. So yeah, there is a slight difference in bankers and this algorithm. In bankers algorithm, we would be checking whether finish of I is equal to true for all. If it is true, then we can say it is in safe state, right? Here we will be checking whether finish of I is false for any of the process, any, not all, any of the process. If finish of I is false for any one process also, then we can say deadlock is there in the system, and that particular process which has not been completed, that particular process is called deadlocked. That particular process is deadlocked. Okay, and this algorithm would require big O of m cross n square time. So the time complexity of this algorithm is big O of m cross n square, which is same as banker's algorithm. Banker's algorithm also takes this much time. The complexity of banker's algorithm is also big O of m cross n square. Is that clear? Yeah. So in the next video, I am going to explain this algorithm with one example. I don't have to explain a single instance of each resource type, right? Because it is very simple. Given a resource allocation graph, you can find the corresponding wait for graph by removing all resource edges and their corresponding nodes. Correct? So I will be explaining this algorithm with one example in the next video. Okay.